Look at this heat sink operating under a heavy load. Traditional linear voltage regulation inherently relies on shedding excess electrical energy as intense heat. This occurs because linear components act as variable resistors. To drop a 12-volt supply down to 5 volts, the regulator simply absorbs the remaining 7 volts, burning off the difference. It is a system built on intentional inefficiency. Power electronics functions differently. Instead of using dissipative resistance to step down power, we use high-speed solid-state switching. The physics are straightforward. A perfect switch has only two states. When fully on, it has zero voltage drop. When fully off, it passes zero current. Since power loss is voltage multiplied by current, the theoretical power loss across a perfect switch is always zero. This animated plot illustrates the mechanism. We generate a high-frequency square wave, rapidly toggling the switch on and off. Passing that chopped waveform through an LC filter, an inductor and capacitor, averages it mathematically into a clean, continuous voltage. This logic translates electrical energy across 4 domains: AC to DC, DC to DC, AC to AC, and DC to AC. Modern power electronics abandons the design of physical resistors. Instead, it relies on algorithmically controlling time to manipulate power without loss. Before we can construct the conversion matrix, we have to define the base physical components, the solid-state switches that make this temporal control possible. This plane plots the VI characteristics of the diode. It's an uncontrolled switch, relying entirely on natural polarity. When the sine wave drops below zero, the diode snaps off. This natural turn-off process is called commutation. The thyristor introduces a level of control. It remains off until a specific gate firing circuit delivers a pulse, shifting it into forward conduction. However, it still relies on natural commutation, a drop in current, to turn off. It is a semi-controlled device. For absolute control, engineers use MOSFETs and IGBTs. These are fully active, fully controlled devices that do not wait for the circuit's natural polarity to shift. To function, MOSFETs and IGBTs require continuous, highly active gate drive circuits. The engineer decides exactly when the switch opens and closes. Progressing from diodes to IGBTs is an evolution from passive observation of a circuit to absolute active command over its current path. We can now populate the first quadrant of our matrix, AC to DC conversion, commonly known as rectification. This schematic shows a 3-phase semi-controlled bridge thyristor rectifier. By using phase angle control to intentionally delay the firing of the thyristors, we can vary the average DC output voltage. Look at the plotted waveform for a purely resistive load. The current rigidly follows the voltage waveform. The moment voltage drops to zero, the current stops. But industrial applications complicate this. Real-world loads, like massive motors and transformers, are rarely pure resistors. They are highly inductive. An inductor resists changes in current flow. Think of this heavy steel flywheel. Even when the driving mechanism pulls away, physical inertia keeps it spinning. When we swap the purely resistive load for a highly inductive RL load, electrical inertia forces the current to freewheel. It smooths out into a continuous, flat forward line, ignoring the negative voltage steps from the source. This inductive inertia keeps the current flowing, which severely degrades the input power factor and delays the natural commutation of the thyristors. The nature of the load dictates the required control logic of the source. That brings us to the second quadrant of the matrix, DC to DC conversion, achieved through elementary chopper circuits. The primary operational lever in this domain is the duty ratio, represented as D. It is the exact percentage of time the active switch is closed during a single cycle. This buck converter steps down voltage by fracturing the DC input. As the slider drops below 1, the switch spends less time closed, and the averaged output voltage line drops proportionally. If we rearrange that exact same active switch and diode, we create a boost converter. Now the closed switch stores energy in an inductor. When it opens, that stored energy stacks on top of the input, stepping the output voltage up above the source level. Combining these two topologies yields a buck boost converter, a single circuit capable of both stepping up and stepping down the supply. Cautionary: These duty ratio formulas only calculate accurately if the circuit operates in continuous conduction mode. As this graph shows, the inductor current oscillates in a sawtooth pattern, but it must never bottom out at zero during the switching cycle. This precise method of time slicing is also applied to AC cycloconverters, allowing us to alter alternating voltage without relying on heavy magnetic transformers. In both DC-DC and AC-AC systems, the physical components remain static. The variable that governs the output is the mathematical ratio of time. We now enter the most complex quadrant of the matrix, DC to AC inversion, starting with a single-phase voltage source inverter. The easiest way to invert direct current is to take an H-bridge of switches and throw them back and forth 60 times a second. This produces a crude alternating square wave, but square waves are saturated with low-order harmonics. Feeding that signal into sensitive AC machinery will cause overheating and physical damage. To solve this, we use sinusoidal pulse width modulation, or SPWM. This plot shows the control strategy. We overlay a high-frequency triangular carrier wave with a 60 Hz sinusoidal reference wave. Every time the reference wave calculates mathematically higher than the triangular carrier wave, the system fires a gate pulse. This generates a sequence of square pulses that are widest at the peak of the sine wave and narrowest at the zero crossings. The ratio between the amplitudes of these two intersecting waves is defined as the modulation index. Adjusting the modulation index directly controls the output voltage of the inverter, and this holds true whether the system is programmed to operate in unipolar or bipolar modes. SPWM proves that we can synthesize a smooth analog output using high-frequency digital on and off switching. To drive heavy industrial motors, the single-phase H-bridge must be scaled up into a three-phase voltage source inverter. Look at this topology. Managing 6 active switches across 3 phases requires immense temporal precision to maintain a balanced, rotating magnetic field in the load. We can run this inverter in a 180-degree conduction mode, where each switch conducts for exactly half a cycle. But 180-degree mode has a fatal flaw. When an upper and lower switch on the same vertical leg transition simultaneously, there is a split-second overlap where both are on. This creates a catastrophic shoot-through short circuit that bypasses the load entirely. Engineers solve this by utilizing a 120-degree conduction mode instead. By mathematically forcing a 60-degree dead time gap between an upper switch turning off and a lower switch turning on, shoot-through becomes physically impossible. As power topology scales up in complexity, circuit protection relies entirely on the absolute sub-millisecond control of commutation timing. This is the completed universal conversion matrix. By isolating and mastering these topologies, we have mathematically synthesized power across all 4 fundamental domains. In the inverter domain, the final architectural choice depends on the power source. The voltage source inverter, or VSI, requires a stiff DC voltage maintained by a parallel capacitor. The current source inverter, or CSI, requires a stiff DC current maintained by a series inductor. Because batteries and standard electrical grids naturally provide stiff voltage, the VSI is the standard architecture for most applications. The CSI is highly specialized, reserved for specific high-power motor drives. We started with a wildly inefficient linear resistor, burning off valuable power as heat. We replaced it with fully controlled semiconductors, MOSFETs and IGBTs, and governed their operation through exact duty ratios and precise modulation indices. Electrical engineering at this level is no longer about routing power through physical barriers. It is the art of mathematically commanding time to move energy with near total precision.